All right, in this quiz, we're going to be looking more at parts of an atom and some of the significance of the experiments that got us here. So the first question is asking, what are the three parts of an atom and what are their properties? And this is kind of a broadly asked question, but I think there are really two properties for all the subatomic particles that are really, really important understanding and for knowing what we're really doing moving forward. So what are the three parts, first of all? Well, we have protons, neutrons, and electrons, three trons, right? So protons, neutrons, and electrons, what makes up these different particles? What makes them different? And for a proton, what we should know about these is that they have positive charge, they do have mass, and they're located in the nucleus. And as we've studied the values of like how much positive charge, how much mass, they do have rather, intricate values if we want to put them in standard units, but we really just consider the numbers whole numbers, right? Protons have a positive charge, +1. They have a mass of 1 atomic mass unit, and being located in the nucleus is really important as well. Neutrons, they have no charge, right? Zero charge, neither positive nor negative. They have mass, same as the protons, and they're also located in the nucleus. The electrons are what carry the negative charge. We consider them massless, which is not entirely true, but it's so small compared to the protons and neutrons, we basically say the mass of an atom or an element is due to its protons and neutrons. And importantly, the electrons are located outside the nucleus. So these properties, the charge, the mass, and I guess where they're located is really what I'm going at when looking at these properties of protons, neutrons, and electrons. Okay, part B says conservation of mass states that the total mass is always equal to the total mass of the reactants. And we want to know, is this always true or is this only sometimes true? And so in this case, what we want to recognize is that this is pretty much always true. You know, for classical chemistry, this is true, right? This is conservation of mass. We want to say that it is going to be the mass of the reactants equals the mass of the products. And we do see some exceptions in nuclear chemistry, which we're not talking about really right now. You know, nuclear fusion, nuclear fission. Mass is not 100% conserved, but it's nearly all conserved. And for most experiments, this is going to be absolutely true. You know, unless we're doing some breakdown of the nuclei, we're not going to have any loss of mass. Conservation of mass will hold true. Okay, so now what about if we say, well, if we have two atoms, do they always pair in the same ratio? And we want to support why or why not with an example. And this is to say, if we have carbon and oxygen, do they always combine in like a 5-to-4 ratio or a 1-to-1 ratio, right? Just by virtue of having one atom and another, are we going to have the same ratio? And the answer here is that this is not true, that atoms often pair with multiple ratios. We can have really many numbers of many combinations of binary covalent molecules. So a good example here is carbon dioxide, right? CO2 versus CO. Carbon and oxygen, both of these, but in the first case, we have a 1-to-2 ratio, carbon dioxide, and in the second, we have a 1-to-1 ratio, carbon monoxide. And this gives us two different molecules with two different ratios. Another example is water versus hydrogen peroxide, H2O versus H2O2. This is another example of molecules that will have different ratios. They're just two different molecules, right? Just by virtue of having hydrogen and oxygen, we're not always going to come up with water. All right, last question is saying, in the oil drop experiment that we looked at, it was shown only specific amounts of charge were applied. Why do we even care? You know, the idea that it's only discrete amounts of charge that are shown is the big success from the oil drop experiment. And this is significant because what we demonstrate is that the negative charge is in discrete packages. It's not continuous. You know, we don't paint on an amount of negative charge, but we kind of set it like bricks on a cart, right? Does it have 3 bricks worth of negative charge or 5 bricks? The fact that we don't have any negative charge that's showing itself as like 2 1/3 bricks or 5 1/2 bricks shows that whenever we're putting negative charge on something, it's going to be in whole number amounts of these packages. And these packages, it turns out, is the electron. That was the conclusion, and that's what's held up over time, that these packages of charge are the electron. And so not only was it to demonstrate the existence of this quantized negative charge, this package of charge that is applied to our ions or whatever, our oil drops, which is a really important principle that we're going to look at in this course. As we see things losing charge and gaining charge, it'll always be in terms of a whole number of electrons. That is really significant. And in addition to that, it determined the charge of an electron, which is equal to the positive charge on a proton, the magnitude, and it even got it in terms of our standard unit in a way that we're going to be able to do more calculations further on in chemistry, this course and otherwise.